Okay, so the final module is where we summarize what we have learned about integral equations so far, and this is going to be the outline. Two main methods that we have seen are surface and volume integrals. So, we will just list out the differences between them. The new concept over here is going to be that of the radar cross section, okay, which is abbreviated as RCS. So, that is like all the theory that we have learned, how do we finally put it into use to calculate something that is useful. Okay. And a small word about what are some of the computational issues that you will face in this. Okay. So, before we go into surface and the difference between surface and volume, I want to take a quick aside. One sec. About surface integral equations in the presence of PECs. So, what is a PEC? A PEC is a perfect electric conductor. Okay. So, a perfect electric conductor is one which colloquially you will call like a perfect metal. So, what is the property of a perfect metal? That conductivity is infinite. Therefore, we have studied all of this before, right? Charges do not reside in the volume, they all go to the surface, right. So, in the formulation that we had so far, which is shown over here, this was our original formulation. We had given a physical interpretation to the variables, right. So, when I looked at TM polarization, so what was my phi? What physical quantity was my phi? Electric field, right. So, particularly phi was E, the z component, right, and grad phi dot n hat we had given an interpretation as what was it proportional to? We had worked it out, it was proportional to the H tangential on the surface. Okay. So, we had interpreted these equations as a sort of a linear combination of the tangential electric and magnetic fields. Okay. This was in TM polarization. Similarly, if you did for TE polarization, you would get E tangential and HZ. Okay. So, if the conductor is made, if the object is made out of a perfect electric conductor, what are the, should we just use these system of equations as is, or should we change them somehow? So, what are the boundary conditions? What do boundary conditions for PEC say? Are any of these two guys 0 or both are non-zero? E tangential, right. So, remember this was my problem, right. So, Z was coming out of the board, that was my Z axis, and Ez is which way? It is purely along the surface of the conductor that is coming out of the plane. So, Ez is going to be 0 because on a perfect metal the surface the fields are always what? Normal. Purely normal, right. So, the fields are always normal, but so in TM polarization E is forced to be Ez and H is xy plane. So, therefore, there is going to be no component of electric field in the z direction in TM polarization, right. So, for PEC we can say that Ez is equal to 0. Can I say anything about H tan? We can't say anything, right, it will be whatever, it will depend on the problem, right. So, for a PEC Ez is equal to 0. Can you think of any other possibility? Can you think of a possibility where phi is non-zero, but grad phi dot n hat is 0? What kind of a material would it be? PMC, right, that is right. So, if we have a perfect magnetic conductor, in that case H tan will be 0, Ez will not be equal to 0. What is a perfect magnetic conductor, right? It is a hypothetical object. It is just like how in Maxwell's equations earlier we had an electric current but no magnetic current, right, but we added a magnetic current to give symmetry to the system of equations. So, similarly, I just for sake of completeness, if I talk of PEC, I also talk about PMC. Okay. It may be useful if I use some of the equivalence theorems, That is why I am mentioning it over here, because by using equivalence theorems I can introduce a fictitious magnetic current or electric current. So, that is why I am saying that, that is why I want to make a note of it. So, what happens to my system of equations now? Earlier, supposing I broke up this surface into n segments, capital N segments. So, how many variables were there in this equation? How what was the size of the system of equations? 2n cross 2n, right? Now, in the case of PEC, what happens? Is there any, what all terms from here will survive, what will not survive? Right. So, this term over here and this term over here, these are both 0 and 0, right. So, only these two terms survive. So, I will just have G1 R prime grad phi dot n hat, right, dl is equal to phi I of r prime, and G2 of R prime grad phi of r dot n hat dl is equal to 0. So, this is going to give me a n cross n system, right. So, in some sense it is a easier problem to solve. Can you tell me one more reason why it is easier than the earlier system of equations? Which term did I not have to worry about? Grad g dot n hat. And was there a particular problem with grad g dot n hat? The singularity caused more of a trouble with grad g dot n hat. I had to be very careful how I integrated. I got plus half or minus half. But for a perfect electric conductor, that problem is not there, because the grad g term is gone away. I am just left with g, and g had a singularity which was integrable. Okay. So, this is how you would this is how you would solve a problem with a perfect metallic conductor, perfect electric conductor. Okay. So, in some sense it is the easier thing. We could have started the whole discussion with PEC and then built it to dielectric objects, but we have done it the other way.